Hi guys, how you doing? Okay, we're going to do the derivative of constant multiple rule. Now, I want to remind you of your limits. Do you remember all your limit properties? Well, we need them. Why do we need them? Because you remember what derivatives are? Derivatives are limits. Someone asked me once, what do limits have to do with derivatives? You know what my answer is? Everything. A derivative is a limit. It's just the way it is. So any limit properties you have correspond to derivative properties. I think that makes sense. Okay? So we had a limit property once that said if I had a constant times a function, and I was asking for the limit of a constant times a function, that was simply equal to the constant times the limit of the function, which gives us this one, this one, okay? So what we're going to do now is we're going to ask for a derivative. I'm going to ask for a derivative of a constant times a function. Well, that'll be equal to the constant times the derivative of the function itself, which will be and we're going to get so good at this that when we see this, what we're going to do is just bring the 2 down, multiply it by the other 2, and get 4, and it'll just be x. So just to show you how it's going to play out, this is going to become, because the 3 came down, multiplied by the 5, got 15, I took 1 away from the exponent. That's it. This is the derivative function for that curve. That's it. So what does this do? And I want to take a minute and just talk about this again. But this is what I've done. Up until now, if I wanted to know the slope of the tangent to a function, f of x, okay, so if I want to know the slope of a tangent of a function f of x who equaled 2x squared, or sure, we'll do 2x squared. So what happened was, in the past, you had to do this. Limit as h approaches 0 of f of x plus h minus f of x over h. Now, f of x was equal to 2x squared. F of x plus h was equal to 2x plus h squared. So this limit as h approaches 0, which I can also call the derivative function, is equal to 2x plus h squared minus 2x squared over h. Limit as h approaches 0, 2x squared plus 2xh plus h squared minus 2x squared over h. Expand the 2 in. Limit h approaches 0 of 2x squared plus 4xh plus 2h squared minus 2x squared over h. X squared, 2x squared, 2x squareds. So I have an h value. I'm going to common factor it out. Limit as h approaches 0 of h of 4x plus 2h over h. H over h, notice that neither one is 0. So that's good. That leaves me with the limit as h approaches 0 of 4x plus 2h. Ring-da-da-ding, ring-da-da-ding. Smaller, 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 smaller. Eventually it approaches 0. So we get left with 4x. So the slope of the tangent anywhere to the function f of x equals 2x squared is equal to 4x. Well, wait a second here. If I use the derivative of a constant here, if I know that the derivative of 2x squared by dx, bring the 2 down, multiply by 2, it's going to be 4x. Oh, wait a second. I just got this answer in one step, and you had me do all of this before? How are they related? They're identical. Yeah. They just are. Some of you are really angry right now, but they just are. And what it means, graphically, is I have f of x equals 2x squared, which means it looks something like that. So any slope of the tangent anywhere is going to be given by 4x. So let's say I pick a value of 3. The slope of the tangent at that point is going to be 3 times 4 is 12. So in other words, if I go over 1, I go up 12. That's the slope of the tangent. Now if I pick another one over here, negative 1, at this point. Now this point is actually negative 1 comma f of negative 1. F of x is actually 2x squared. So this is actually negative 1 comma 2. The slope of the tangent, however, at that point, however, is going to be f prime of negative 1. F prime is 4x, so it's going to be negative 4, which means that I go over 1 and I go down 4, which is the slope of the tangent of this tangent line. Yay! That's how it all comes together, kids. And you want it even worse? What's the derivative curve? So if this is f of x, the derivative curve now will be... Oh, let's do it nice. This is going to be f of x. This is going to be x, and my original one is f of x equals 2x squared. Whee! Let's do my derivative curve. Notice that the slope of the tangent here is 0. So the slope of the tangent here is there. Notice that this slope of the tangent is negative. They're all negative. And it's going from pretty large down to here. So maybe like that. And notice that this is positive, and it's going from 0, and it's getting, wait a second, goes from negative. Ooh, that was bad. Sorry. That's negative. Really, really large negative to 0. That looks like this. And then it goes from 0 to larger and larger and larger positive. That goes like this. Do you remember what the derivative of this was? Bring the 2 down. Take 1 away from the exponent. Does this look like anything? This is the line, over 1, up 4. Okay, so just so that you understand what's happening, let's come back to the question. Determine the derivative of each of the following. Well, I think we've gone over this enough times that we get it. So what's going to happen is the 2 is going to come down. Y prime will be 20x. 2 came down, multiplied by the 10, took 1 away. It doesn't have to be variable x. Could be the variable t. The derivative of s of t is s prime of t. It'll be 12. Bring the 4 over 3 down. T, 4 over 3 minus 1. 12 divided by 3 is 4, times 4 is 16. T, 4 over 3 subtract 3 over 3 is 1/3. That's the way I'd like it written, please. The other way it could be written is 16 cubed root of t, but most people goof that up, and I end up thinking that it's 163 times root t. So be careful. We like this form better. And this one, there's my constant, there's my function. It's got an invisible 1 there. The 1 comes down, multiplies by the 5 to get 5. 1 subtract 1 is 0, so it's x to the 0, which is 1. So the answer is 5. And once again, let's give this a thought. 5, if this is y equals x, then that could be y equals 5x, and you'll notice that has a slope of over 1 up 5 everywhere along there, which is what this is saying. Okay, limit properties once again. The limit as x approaches 3x of 5, let's not do that, we haven't even got there. The limit as x approaches 5 of 3x squared plus 7x. So the limit of a sum, or difference, is equal to the sum, or difference, of the limits. So the limit of a sum is equal to the sum of the two limits. What that means is that if I have f of x that is made up of two functions, let's say u of x plus v of x, then the derivative of f of x will be the derivative of the first one plus the derivative of the second one. So, using Newton's notation, it's really easy to write the answer. It's going to be 2 down, multiplied by the 2 is 4, take 1 away, it's 1. Bring the 1 down, multiply with the 3, it's negative 3, and x to the 0 is 1. So your answer is 4x minus 1. It's easy to write the answer. It's not so easy to explain to someone what you're doing. That's where Leibniz notation comes in. It's really nice to be able to say, without using words, because words get jumbled. But this says, take the derivative of the first term, and then subtract the derivative of the second term. That's what it says, which is 4x minus 3. Now, do you have to do this? No, but you have to be able to think this, and you have to be able to read this, and you have to be able to write this. But on your test, that's what I'm looking for. Okay. Can't do this one. Doesn't look like anything I know how to handle. Now it does. Take the derivative of the first one. It's going to be 5 times negative 2, x to the negative 3. The next one is going to be plus 1/2, x to the negative 1/2. Where'd you get the negative 1/2? 1/2 subtract 1 is negative 1/2. This will leave you with negative 10 over x to the 3 plus 1 over 2 root x. And that's a perfectly good way to write it. The next one you do not know how to do. You may think you know how to do it, but you do not know how to do it because the bottom is not a singular term. The rule that we have, looking for my rule, the rule that I have is a singular base. You do not have a singular base. So we can get around this by expanding it. Now the derivative of this will be the derivative of the first term, the derivative of the second term, and the derivative of the third term. If you wanted to write that so people understood it, you would write this. Would I write this if I was just doing it for homework? Oh, I ran out of room. 25. There, does that look like 25? Hey, it does too. Okay, so the derivative of the first one is 8x. The second one plus 20, and the last one is 0. So it's simply going to be 8x plus 20. Okay, thus endeth the lesson. I'm going to go away and I'm going to come back, and I got one little bit I want you guys to take a look at.